Well, hello again. Today I'm going to talk about standing waves on a string and in pipes with the goal of helping us understand musical instruments. So, standing waves. So first, standing waves on a string. So I'm going to suspend, I'm going to tie a string between two rigid supports. It could be two poles or two walls. So here's a string, and I'm going to look at multiple situations. I'm going to vibrate this string at different frequencies, and at certain frequencies, because of resonance, the string will have a larger amplitude vibration. So the first case where that happens, the string will vibrate with a shape like this, where it has one antinode in the middle and a node at each end. It has to have a node at each end because it's tied there. Notice that this particular case, this is half of a wavelength. I would have to extend this on out to have a whole wavelength, because a whole wavelength would look like up and down and back up again. That would be a whole wavelength. So this is a half wavelength. If this has length L, then I note the length of the string is 1/2 of a wavelength. The next case that has a node at each end would have a shape like this. That's a whole wavelength, but I'm going to note that it has two of these loops, has an antinode and an antinode. So I'm going to note L is 2/2 of a wavelength. But since this wavelength is different than that wavelength, I need to somehow note that. So I'm going to call this wavelength 1 and that wavelength 2. The next case, they could have a node here and a node here, would look like this. Now I've got 3/2 of a wavelength, and I write L is 3/2 of wavelength 3. And then the next case would be like this. I've got 1, 2, 3, 4. L is 4/2, and that's yet another wavelength. I'm going to call that wavelength 4. And you see that this would go on. The next would be L is 5/2 of wavelength 5. So we see a pattern that the possible standing waves on this string would look like the length of the string is some n/2 lambda n. Or if we want to know the wavelengths, the nth wavelength is 2L/n, where n is an integer, 1, 2, 3, 4, etc. Now, in talking about musical instruments, we usually talk in terms of frequency and not wavelength. So let's think about what the frequencies would be. We know V is lambda F, where V is the velocity of a wave on the string. So the frequency would be V over lambda. Lambda is this, so this would be V over 2L/n. When you divide by a fraction, you multiply by the reciprocal, so this is n times V over 2L. But 2L is the first wavelength, because when n is 1, we get lambda 1 is 2L. So V over 2L is just the first frequency, and we just get that the nth frequency is n times the first frequency. So you can see that from here. V is lambda F, so F1 is V over lambda 1, but lambda 1 is just 2L, that's V over 2L, which is what we had there. So Fn is n times F1. That's a system we say is harmonic, when the frequencies are just multiples of one another. So if this is 100 hertz, this would be 200 hertz, 300 hertz, 400 hertz. Strings behave that way. That's what makes them so excellent in music, part of what makes them so excellent in musical instruments, like your piano, your violin, your cello, etc. So let's do an example. In order to do an example, we have to know the velocity of a wave on a string. We haven't done that. So the velocity of a wave on a string is given by the square root of the tension over something called the mass density. So this is really just an aside so we can get that velocity. The mass density of the string is the mass of the string over the length of the string. So this is not a super important formula. This is just something that tells us the velocity of a wave on a string in tension. So, for example, what are first 4 frequencies? We actually call those the harmonics. For a 4-gram string under 80 newtons of tension. We have to know how long it is too. Let's say it be a 2-meter string, 2-meter long. All right, well, in order to do this, I have to know the velocity. To get the velocity, I have to know mu. So mu is its mass, 0.002 kilogram, nope, 0.004 kilograms. I said it was 4 grams over 2 meters. That's 0.002 kilograms per meter. The velocity is the square root of the tension, 80 newtons, over 0.002 kilograms per meter. That's 200 meters per second. So that was really just an aside, just to find that velocity so we could talk about the more important issues here. So the first frequency is V over 2L. We saw this here. That's 200 meters per second over 2 times the length of the string, which was 2 meters, because I just chose it to be 2 meters. That's 50 hertz. 200 over 4 is 50. And then since these just go as N times F1, F2 is 2 times 50, which is 100 hertz. F3 is 3 times 50, which is 150 hertz. F4 is 200 hertz, etc. So those are what we call the harmonics of this system. So if this is 50 hertz, this is 100, this is 150, this is 200, etc. Those are the possible standing waves that this string could vibrate in. If this were a musical instrument, say a string of a violin, this would be called its fundamental, but even when it vibrates at this frequency, it has mixtures of these other frequencies vibrating as well, and that is much of what gives that instrument its timbre, its quality of sound. All right, so that's our standing waves on a string. They're harmonic. They're multiples of some fundamental frequency. By the way, in music, sometimes we use another nomenclature. So this is the first harmonic, the second harmonic, the third harmonic. Sometimes this is called the fundamental, the first overtone, the second overtone, the third overtone, etc. Okay. Next, I'm going to talk about standing waves in pipes so that we can understand other musical instruments, things like organ pipes, for example, if you just want to picture one, or something like a flute. And there's a couple ways these pipes are done. One, we can have an open pipe or a closed pipe, and by open we mean open at both ends. When we say an open pipe, that's what we mean. And it's going to look very, very like what we just saw. So I'm going to draw some pipes. So here's a pipe. Here's another pipe. Here's another pipe. So here's another pipe. And it has length L. Now I'm going to show you the possible standing waves in a pipe. Now in a pipe, there has to be an antinode at the end. That's not completely obvious, and I don't have time to go into it right now, but there has to be an antinode at the end, and so the first possibility looks something like this. And the next possibility with an antinode at each end looks something like this. The next possibility like this. And then, let's see, I've got 1, 2, 3. 1, 2, 3, 4. Next one looks like this. Etc. So now what have we got? Notice this is, again, half of a wavelength. This is a quarter of a wavelength. How do I know? To get an entire wavelength, I need 2 complete loops. So that will be an entire wavelength. So this is a quarter of a wavelength plus a quarter of a wavelength makes half of a wavelength. So here I've got the length is 1/2 of lambda 1. Here I've got a half of a wavelength, another quarter and another quarter. So again, I've got a half plus a quarter is 2 halves. Length is 2 halves of lambda 2. 1/2, 1/2, another half, 3 halves. Length is 3 halves. Lambda 3. 1/2, 2 halves, 3 halves, 4 halves. Lambda 4. And I've got the same progression I had a moment ago. So I've got length is n halves, lambda n, where n is 1, 2, 3, 4, etc. Where lambda n is 2l over n, where n is 1, 2, 3, 4, n is an integer. And I could go through the same logic I went through a moment ago, and at the same time I'll just write the conclusion since I just went through it. We would again get Fn is n F1, where F1 would be V over 2L, just like we saw. But V is now the velocity of the wave, which it was in the other case too, but it was a wave on a string. This is the velocity of a wave in air, so now V is our 331 meters per second, square root of t over 273, because it's the wave is now in air. So an example, suppose at 20 degrees C, you have a pipe that is 75 centimeters long. So about like that, so roughly the size of some musical instruments. So what are its harmonic frequencies? Okay, we need F1. F1 is V over 2L, so we need V. You could do this, so we plug in 20 in here, so 270, so this is 331 square root of 273 plus 20 over 273, and we would get 343 meters per second over 2 times 0.75. This gives me 228.7 hertz. So that's close to the A below middle C on a piano. The A below middle C is about 220 hertz. F2 would be 2 times that, is 457.3 hertz. F3 would be 3 times that, (686.1 hertz), etc. So again, if you had an instrument where its fundamental was 228.7 hertz, when you played that note, it's unlikely that it would produce just this. It would have this standing wave in it, and some of this one, and some of this one, and some of this one, and that mix of standing waves is much of what gives it its timbre, what gives it its quality of sound, what makes that instrument sound like that instrument, or makes a flute sound like a flute, for example. All right, so that's a pipe that's open at both ends. Now I'm going to do a pipe that's closed at one end. So I'm going to write down my results for this because I want to compare them. We're going to get a different answer. So I'm going to remind you that F1 was 228.7 hertz. F2 was 457.3 hertz. F3 was 686.1 hertz. I just want to remember what those were for our 75 centimeter pipe. So now, let's look at a pipe that is closed at one end. It's kind of nice to have one end open so the sound can get out. So closed at one end has to have an antinode at the open end and a node at the closed end. So the first case looks like this. The next case looks like this. It's kind of like a fish. Next case looks like this. Etc. This is now just a quarter of a wavelength. We've got half of a loop. It's just a quarter of a wavelength. So L is 1/4 of a wavelength. Call that lambda 1. Now we've got, let's see, here's a quarter, here's a quarter, here's a quarter. We've got 3/4 of a wavelength. We'd have to add one more quarter to get a whole wavelength. So L is 3/4 of a wavelength. And I don't want to call that lambda 2. That turns out that'll mix up my notation. You'll see why later. I'm going to call that lambda 3. Here I've got 2 quarters, 4 quarters, 5 quarters. L is 5/4 of lambda 5. 2, 4, 6, 7. L is 7/4 of lambda 7, etc. Or in general, the nth lambda is 4L over N, where N is not all the integers. It's just the odd ones, 1, 3, 5, 7, etc. The even integers are missing when you close one end. Now our other logic works about the same. If we would still have V is lambda F, we would still get Fn is in F1, but F1 would now be V over 4L, because lambda 1 is 4L, because lambda 1 equals 4L. And so even though we have Fn is in F1, the ends are 1, 3, 5, 7. The even harmonics don't occur in a pipe closed at one end. So let's think about our pipe we had our 75 centimeter pipe. Let's take that same pipe, but let's close one end of it and see what frequencies we get. So 75 centimeters long at 20 degrees C, the same temperature. That implies V will be 343 meters per second. Now F1 will be V over 4L, will be 343 meters per second over 4 times 0.75 meters. That's 114.3 hertz. Notice our F1 before we close it was 228 hertz. This is half that. So this is an octave below that. So this plays a lower note. Even though it's the same length, it's a lower note. It sounds more bass. F2 doesn't exist. F3 is 3F1, is 3 times 114.3 hertz, is 343.0 hertz. F4 doesn't exist. F5 is 5 times 114.3. Which is 571.6 hertz. So this instrument, even though it's the same length, plays a lower pitch and a different mix of harmonics. If you made it a length so that even if it played the same fundamental, it would still sound different because it would have the even harmonics missing. It would just play the odd harmonics. So even if you made the length different than the length we had earlier so that it played the same fundamental, it still wouldn't sound like the same instrument because they have different harmonics mixed in. Well, we'll practice that in class. Your in-class assignment will have, we'll practice that very thing about comparing an open pipe to a closed pipe. So I'll see you soon.